So we're going to talk about mole fraction in terms of pressure. And you already know what pressure is, right? N equals P, well, PV equals nRT, and you can solve it for N to solve for number of moles. Now, what if you want a mole fraction? What do you think that means?
Like a moles together?
Like a part of a total, right?
Like
you're looking at one
composition.
thing. Yeah, exactly. Like percent composition, except this happens to be a fraction. Okay?
Wait, what is it derived proportional to? So it's kind of like percent composition?
Yeah. So you're looking at part of one out of an entire complete thing. Okay?
Like how many moles of CnCH3?
Alright, so you're looking at maybe just one of those out of the entire mixture of gases. Okay. So then, the thing about that is it's directly proportional or directly related to the partial pressures of the gas. So mole fraction and partial pressure are directly related to each other.
So what's that equation at the top?
These are your mole fractions.
What is x of 1 stand for?
The mole fraction. Mole fraction is x. And then now this is x in terms of pressure. Okay? And since you're looking at the pressure, you can look at it in terms of partial pressure. So this is really based on a mixture of gases, like the air, right? The air is made up of oxygen, it's made up of nitrogen, and then you have, maybe a little bit of water vapor, a little bit of carbon dioxide, and so on. So you're looking at a total part over a total.
So are those
Okay?
two equations the same as?
They're equal to each other, right? Okay. So now let's look at this. The partial pressure of oxygen was observed to be 156 torr in air, and the total atmospheric pressure of air happens to be 743 torr.
So you just divide.
So can you find mole fraction of oxygen? So oxygen within the atmosphere, it's only one of the gases, right?
156.
Okay. So how would you go about it?
You just divide 156 divided by 743.
Yep. Okay. So we just said mole fraction is directly related to partial pressure, right? So if you have partial pressure of oxygen, which happens to be 156, total atmospheric pressure happens to be 743. So the fraction of the partial pressure is the same as the mole fraction. Okay? Does that make sense?
So you can either do the mole out of the total moles or the partial
Right.
pressure.
Since you're not given the moles in this case, you're just given pressures, you work with just the pressures to find the mole fraction. Okay? And mole fraction, of course, has no units because you're canceling them all out.
So when we write the mole fractions, just write something over something.
Right, so it's going to be X. Mole fractions are represented by X. Partial pressures are represented by P with their subscripts. Okay? So you can rearrange the partial pressure to be a mole fraction and the partial pressure and the total pressure.
X times the pressure of the total.
Yeah. Doesn't make sense.
So
Why is there a plus there? That shouldn't be a plus, guys. That should be a times.
that's what I was trying to
Just
figure
Yeah, it has to be
Just flip it like 45 degrees.
Yeah, I think that's just a typo. Yes.
So why do they say like x2 equals, when they say x1 it's for the pressure, and then for the other equation it's like x2?
It's any gas.
Okay.
So when you're dealing with the actual gas, you would write like XO2 or something like that on the bottom. Okay. Now, certain gases are collected over water. Okay? So when you're collecting a gas over water, you have to take into consideration the water vapor pressure. So what that means, let's look at this. So here you have potassium chlorate, and you're going to decompose potassium chlorate. When you decompose potassium chlorate, one of the gases, well, the only gas that is produced is oxygen. Okay? And you collect it over water. So you're collecting this gas in the presence of water. So there's water vapor pressure that interferes with the pressure of this system. Okay? So for that reason, when we're dealing with gases collected over water, we have to deal with the water vapor pressure. And I'll show you a problem so you understand how that works.
You have to like subtract it.
Yeah. Basically, you have to get rid of the water vapor pressure from the actual pressure. I'll tell you how that works. So here we have, hold on. Here we have potassium chlorate. Potassium chlorate decomposes, you're going to get potassium chloride, which is your solid product, and oxygen gas, right? The oxygen that is being produced is collected by displacement of water at 22 degrees Celsius, total atmospheric pressure of 754. The volume that was produced from the oxygen was 0.650, and the water vapor pressure at 22 degrees Celsius happens to be 21 torr. Okay? Knowing all that, what are we calculating? Well, we're calculating the partial pressure of the oxygen and mass of KClO3. Okay, so let's go back and think about what we have here.
Did you say what we're calculating again?
So, we're going to calculate the partial pressure of oxygen,
Okay.
and we're going to calculate mass of KClO3 produced. Okay? Yeah? All right. So, how are we going to do that?
You want to count? Okay.
Okay. So why is this given to me? 22 degrees Celsius water vapor pressure happens to be 21 torr. What do we want to do with 21 torr?
Convert it to Kelvin. Not Kelvin, ATM.
Why?
Because,
I mean, you can convert it later. You can convert both of them to ATM, okay? But what are we going to do with 21 torr? So, oxygen is being collected over water, right? So the water vapor pressure is part of the total pressure measured.
Where's the water vapor coming from though in the equation?
Okay, so let's go back. Gas is collected over water.
Mm-hmm.
Okay? So we're basically bubbling the gas into water, and then we're collecting that gas. But as you are doing that, there's also water vapor being produced. When you measure the pressure of the total system, the pressure of the water vapor needs to be removed to find the pressure of the actual gas you're working with. Are you with me? Yeah. Okay. So since you just want the pressure of oxygen, but you have the pressure of the entire system, right? That's not what you want. You want pressure of oxygen. Okay? So what am I doing with 21 torr?
Using it as the pressure of the water.
I don't need water vapor. I don't want water vapor. What do I want? Yes. I want the partial pressure of oxygen. What do I know about Dalton's laws? What's Dalton's law of partial pressures? What does he say? P total equals the, P1 plus P2, whatever. So in this case, P total is equal to the partial pressure of what two gases? Oxygen and water vapor. So if I just want oxygen, what am I doing with water vapor?
From the total.
Yeah. Okay, so that's one.
But it's a solid. That's breaking.
We're not dealing with a solid.
Isn't it?
For now, we're not dealing with a solid. I'm only dealing with oxygen.
So,
And oxygen is a gas.
Yeah.
So then I can have pressure and volume and all that good stuff. Okay? So, in order to solve this problem and find the partial pressure of oxygen, okay? So first thing we're going to do is get rid of that. And that's what we do. 754 was the pressure of the entire system. 21 torr is the partial pressure of water vapor. You subtract the 21 from the 754, and now you're left with 733. So what is 733?
The pressure of water vapor.
No.
the pressure of the
Oxygen.
oxygen.
Oxygen. Okay, it's oxygen you're looking for. Now you have the pressure of oxygen. Can you solve the problem to do everything else that it's asking you to do? What is it asking you to do?
Find the
Mass of?
KClO3.
Okay, so do it. Let's go back. Okay, now you know how to do it. So I'm going to leave the problem up. Okay, and you want the mass of KClO3. So now do it. Resolve. Let's go. Come on.
What are we doing?
You're solving the problem.
Yeah, how?
You do the partial pressure.
That's the part you need to figure out. Let's go. Come on. Yeah, you're thinking. You got it. You know it. You just have to think about it.
To find a number of moles of O2 by using PV for the RT. But it's not at a normal temperature. It's at 20.
If it was at the STP, then you could do the 22.4 liters.
Oh, right. You can still use PV for the RT.
Yep. You use PV equals nRT when it's not at STP. You can use PV equals nRT when it is at STP too. 22.4 is your shortcut.
Wait, but that would be to find moles of oxygen.
Don't you need moles of oxygen to find mass of KClO3?
Yeah. Wait, what's the question?
To find the mass of KClO3.
Okay.
But are we supposed to use the volume of the total gas or just the volume of O2?
Volume of the what?
Because we found the pressure of oxygen gas.
Right.
But we don't know what the volume. Yeah, but that says for the total. Isn't that for.
No, there's no such thing. You can't take out the volume of water, and it doesn't make much of a difference at that. It's negligible, really.
But I always forget my calculator. Wait, you have to convert everything, right?
Everything?
Mm-hmm.
Some things, yes.
Okay.
Not everything.
Oh, Kelvin.
You have to convert the torr, right?
Torr and temperature.
Yeah,
Both?
So you did. Oh, stop.
So you have to convert to an atmosphere?
Because you don't have an ideal gas constant that uses torr. You have one that uses, I think, kilopascal?
What is it?
Yeah. It's
For 1 ATM.
So you do 733 divided by 760. Is that right?
How many different. Oh, 6 things.
Sig figs. How many sig figs you got?
3.
Well,
3?
22 degrees Celsius? Well, if you're going to use it in Kelvin. I guess 3.
What's the mole mass of KCl? Do you know if I can?
KClO3. 133.5. No.
okay.
What's the mole mass of
Yeah, that's kind of
KCl?
what I thought.
133.5.
Yeah,
KClO3 is smaller mass.
What is it?
39.
I'm good at the answer. I got 0.0.
Wait, no.
Yes, sir.
Yeah, just give me a second to find this.
We got a really small number.
Plus.
And then we can, once we get the moles of O2,
Uh-huh.
we multiply it by 2/3.
Then you do multiple mole ratio with oxygen.
So,
And then you find the molar mass of KClO3.
Which is
what's the molar ratio? 2 to 3, right?
yeah
I got 122.55. Wait,
for
moles.
KCl.
Yeah.
What do we want the volume?
What do we want? What?
The mass.
Mass.
Okay.
And 2.1. So that's 2.1.
122.
No, I got 2. How many 6 3? I got 2.16.
Alright, so you got partial pressure of oxygen, right? Bless you.
Thank you.
Then we did number of moles of oxygen from PV equals nRT. So once you have the moles of oxygen, and that should have been 0.964.
Why did I not
Did everyone
know
get that?
No.
Wait, what?
Yeah.
I got 0.264.
Yeah, I got 0.964 atmosphere.
Atmosphere.
Oh, that's
ATM.
just for ATM. That's not the, yeah.
Oh, sorry.
Yeah.
Yeah.
Yeah,
2.59 times 10 to the negative 2, which is 0.0259.
Yeah.
Alright.
Oh, I got different.
And then
It's probably 'cause of
you did the mole-to-mole ratio, right?
Yeah.
And the molar mass of KClO3, 2.12 grams should be your final
I
answer.
got 2.16.
Give or take.
It's probably because of my
Oh.
calculator.
I plugged
And
in
then
the
what
wrong
slide
thing.
is that?
Yes, did everyone get 2.12 or 2.11 or 2.13? Somewhere around that vicinity?
I just messed up with the numbers. But I get it.
It's probably my calculator, not the way.
Questions on how to solve it.
Can you go over a little bit more on the partial pressure, like how we got 733? I didn't quite get that.
You subtract the water vapor from the total. That's it. Alright.
Yeah, I got the
Kinetic molecular theory. We've gone over this back in the day. So, purpose of this theory is to explain the property of an ideal gas. So there are postulates that we look at, which are basically just the points that make up the kinetic molecular theory. And it's kind of like it works in a perfect world for a perfect gas. Doesn't work for many of our real gases. But we'll look at what it's talking about. There's a lot that applies and a lot that can change because of certain properties. So, let's look at the postulates. Number 1 says, particles are so small compared with the distance between them that the volume of the individual particles can be assumed to be 0. So, what does that mean? That means if I look at a single water vapor molecule, one single molecule, I can assume that the volume that single molecule takes up is just negligible. Okay? There's really no way to measure the volume of a single molecule.
As in like O2.
As in a single molecule. Yep.
So you'll say it's 0?
Just can't measure the volume of a single particle.
Nope. Particles are in constant motion. We know that. They're gases, therefore they're constantly moving. As they move, they collide. They collide with the walls of the container that they're in, and they collide with each other. So they bump into each other, they bump into the walls of the container. That exerts pressure, right? Force over a certain area. Particles are assumed to exert no forces on each other. So you're assuming, and this is the part that works well if you're dealing with a non-polar gas, but doesn't work well if you're dealing with a polar gas. So for a non-polar gas, this holds better than a polar one, because you're assuming there are no attractive or repulsive forces between the particles. So no attraction and no repulsion between the particles. Okay? Then you're assuming, which is kind of always the case.
Can we go
that all of this is on the PowerPoint. You guys don't need to copy any of this down. All of this on the PowerPoint. Average kinetic energy is directly proportional to Kelvin temperature. When you're measuring temperature, you're really just measuring the average kinetic energy of the particles. That's all you're measuring.
Yeah.
Okay? So when you're, because that's the movement, right? The faster they move, the higher the temperature.
Yeah.
Okay? Because the faster they're going to move, you're going to see a higher temperature. Right? They take up a lot more space. Alright, so we already talked about pressure and volume relationship, and that was Boyle's law. And what did Boyle say about the relationship between pressure and volume?
They're inversely proportional.
Right, which means?
It's P1, V1 equals P2.
Which means?
Oh, that.
As one
As
increases,
the other decreases.
So if you're going to increase the volume, you're going to decrease pressure.
That's like with the heel.
Decrease volume, increase pressure. Right? So according to the kinetic molecular theory, decrease in volume implies gas particles would hit the wall more often. Right? So it makes sense that if you compress it, they're going to collide more. More collisions mean more pressure. So that's the explanation behind Boyle's law. You understand that Boyle's law is inversely proportional, but what makes pressure increase when you decrease volume is the collision between the molecules. So if you decrease volume, then you're going to get the particles colliding more. More collisions, more pressure. Okay? Now, this is what makes gases compressible. What does it mean for gases to be compressible?
You can like move, you can make a container smaller.
You can bring them to closer together because there's so much space between them. Right? So you can actually compress it enough to turn it into liquid. Right? So the new buses that you see, that you drive behind them, you don't see a whole bunch of smog coming out anymore. And it says fueled by CNG. There's like this little blue sticker and it has CNG. It's compressed natural gas. So natural gas that is used to fuel your homes, like your heaters work on natural gas, your stoves work on natural gas. That gets compressed, and once you compress it under high pressure, you can actually liquefy it. Alright, so this is what this is talking about, right? If you decrease volume, right, so here's a piston, you push on the piston, you're going to see that the molecules get closer to each other. That means they're going to bump into each other more, they're going to bump into the container walls more, and that's going to cause increase in pressure. You had a question?
Yeah. When it says to the Kelvin temperature of the gas, does it?
We're always looking at the Kelvin temperature scale. There's no Celsius scale on the gas laws because it doesn't make sense on the... The reason for that, when you increase the temperature by 1 degree, you actually increase volume by 1/273 of its original volume. It's not a 1-to-1 ratio. Like if you do the pressure and volume, if you double pressure, you half volume, right? It doesn't work that way with temperature.
So it's because of the units, not because.
Yep. Alright, according to ideal gas law, which you already know, the pressure is directly proportional to temperature, right? So now tell me why pressure and temperature can be directly proportional to each other. Explain it in terms of kinetic molecular theory.
Because as there's more pressure, they have to move faster, causing the temperature to go up.
As there's more temperature, they move faster, which causes the pressure to go up.
The temperature and pressure are proportional.
Right. That's really Gay-Lussac's law. For some reason, your books don't mention his name, but it is originally his law. Okay, so you're keeping volume constant, right? You see that the volume isn't changing in these two conditions. So as you're increasing temperature, though, you're going to cause the gas molecules to move faster. If they move faster, they collide with each other, and they collide with the walls of the container, hence increasing pressure.
But if you increase temperature, they move faster.
Yes. So volume and temperature, according to the ideal gas law, you already know that the volume is directly proportional to temperature, again on the Kelvin scale. So why? Why is volume and temperature directly proportional?
Because the volume is on the left side and temperature. Do you mean explain it in terms of
What happens to volume when you change temperature?
when you
When you increase the temperature, the volume increases.
Why?
Spread farther.
Right. They move faster, they spread farther apart. That's it. Okay, that's what that looks like. Volume and number of moles, what is the relationship? More moles
the
you
more
have,
moles, the more space.
the more space it can take up. There you go.
But what if
It's
you have,
less.
like more moles but less, but the temperature is less?
Okay, now when you start changing a whole bunch of things, then that's why you plug it into PV equals nRT or the combined gas law, P1 V1 over T, to try to figure out what really happens, right? Because it depends on how much you're increasing, how much you're decreasing to see what the volume change or pressure change might be.
So when moles go up, volume goes up too.
Yeah, because you just have more molecules mean more space. Yes,
What are the
volume is V. R is the ideal gas constant, right? That's the 0.08206 that's on your sheet. T is temperature in Kelvin. P is pressure in ATM. N is number of moles.
and the R is always the same?
Always the same.
They also put it on here.
Yeah,
Like
it's
this
on the
one.
sheet.
They give the constant liters of STP.
Yeah, I believe so. Or they give actual STP conditions. Okay. Remember we were talking about like CO2 cylinders yesterday?
That's
The
after-
soda streams, right?
One thing they don't give.
Then you can release the pressure and release volume from there.
They don't give the liters. They just give you Kelvin and ATM.
That's good enough. You can always plug into PV equals nRT. All right. So KMT, which is kinetic molecular theory, assumes all particles are independent of each other, which means they're not in any way affecting, influencing each other, and the volume of a single individual particle is not important. So those are the assumptions that go with the kinetic molecular theory, kind of the general assumptions that apply to all the postulates. Okay? We don't need to worry about this formula, but pressure can be expressed differently by applying velocity, momentum, force, and pressure, which you can look at in physics.
Oh, thank God.
Thank you, Mr. Harris. He can deal with that part.
I never take
never
physics
take
in
physics.
I don't want to.
Okay. Now, what are all these things, though? Who knows what the kinetic energy formula is?
K equals 1 half mv. What?
K equals M.
Half mv squared.
Yeah, sorry.
Okay. What is m?
Mass.
V?
Velocity.
Okay.
Volume,
Velocity. It's lowercase v. Capital V is volume, lowercase is velocity. Okay?
This is for
So, this is for kinetic energy. What does kinetic energy have anything to do with gases?
Because they're moving.
and
Yep.
that changes the.
Their motion. So, faster they move,
More kinetic energy.
more kinetic energy they're going to have, right? Even if it's a tiny little mass, it can still have a lot of kinetic energy based on its motion, right? Okay?
So the equation is.
So, half mv squared. The reason we're going to look at that is because we're going to look at Graham's law. We're not going to derive it this way. We're not going to deal with that. We'll look at the end point.
What does KE stand
Kinetic energy. Okay.
1/2.
Half mv squared. I'm going to skip all this because we're not going to care about this stuff.
And-
Oh, by the way, this is why R, the 8.3145 you see, has to do with joules. Joules are energy. Okay, joules are a measure of energy, which we'll look at joules more later on, especially when we're dealing with equilibrium and all that good stuff. But joules conversion is kilogram meter squared per second squared.
So do we need to know the root mean square root?
We'll look at the root mean square in terms of Graham's law, but nothing really.
So 1/2 mv squared, is it volume and pressure, or is it velocity and?
Velocity and mass.
Mass of the thing.
So
Yeah, we don't care about
mv squared, so v is
this.
velocity, not.
Yeah.
And what's m? What's p? And p.
There's no p there.
1/2 mv.
Half mv squared. K is half mv
And
squared.
that's to find the kinetic energy of the
Mhm.
molecule.
They wrote like U squared and they said that doesn't.
Yeah, I don't know why they use U. I'm sure they have a reason for it. Okay, so now let's look at velocity and why that is important in terms of gases. Okay, we know why it's important in terms of physics, but we got to know how it's important in terms of molecules and their motion. So, real gases have large number of collisions between the particles. The path of a gas particle is erratic. What does that mean?
Doesn't go straight.
It doesn't have a specific path, right? It's all over the place. Average distance traveled by a particle between collisions in a gas sample is the mean free path, which we're not calculating because we're just not calculating. However, we can look at graphs to kind of figure out what's going on. So when particles collide and exchange kinetic energy, because you have transfer but no loss or gain of kinetic energy, you have a large range of velocities being produced. And that plot right there, the number of oxygen molecules and the x-axis is molecular velocity, shows you that it ranges anywhere from 0 to 8 times 10 to the 2 meters per second. Okay, that's just their speed. That's what they're covering. Now, as temperature increases, the range becomes even larger. Okay? That would make sense. So if the temperature increases, what's going to happen to the molecules?
Move faster.
They're going to move faster, they're going to bump into each other, and then one is going to move slower, one is going to, move faster because it's going to transfer momentum from one to the other, and so on.
So the higher the heat, the lower the volume essentially.
Well, the peaks might be different because the peak reflects the probable velocity, right? But the range is greater. Mm-hmm. Now, knowing that, then we can define 2 important properties of gases. Diffusion and effusion. To diffuse, everyone should know what diffusion is by now, right? What does it mean for something to diffuse? Go from high concentration to low, which is a spreading out until everything is kind of evened out, right? And you do a lot of that diffusion stuff with biology, right? Osmosis and all that. This is in terms of gases, same concept. It mixes, it moves from high concentration to low. What's the difference between that and effusion? Effusion is passing through a small opening under high pressure. You get a hole in your tire, and then you have these gas molecules escaping through that pinhole.
Like a balloon.
Right? Like a balloon. So it's escaping of the gases, passage of gas through a tiny orifice. Orifice is an opening into an evacuated chamber. The rate of effusion measures the speed at which the gases are transferred.
It's like controlled diffusion.
How do we find the rate of diffusion?
It's based on molar mass.
Isn't
That's all it
Grahm's
is. Yeah, it's Graham's law. Yeah.
Also,
That's the worst law
those
ever.
graphs, were those like for just like
the rate of
examples?
Yeah. Okay. So here's a gas molecule right on the left side of this chamber. Here's a pinhole, right? A tiny little hole, ladies. And here's a vacuum chamber, right? So the measurement of that, the measurement of which those gases passing through the pinhole is going to be your rate of effusion. Rate of effusion is based on molar masses. Why? What was kinetic energy based on? What is the formula for kinetic energy?
The mass.
Half mv squared.
Oh, so the mass.
So kinetic energy is based on mass. That same concept, right? The rate at which a gas effuses is based on its molar mass. The heavier the gas, what?
The slower.
The slower it moves. Okay? So, the rate of effusion is inversely proportional to the square root of the molar mass. Again, think of half mv squared, deriving the formula from the half mv squared, and that's where the radical or the square root comes from. So, the rate of effusion is inversely proportional to the molar mass, and that's why it's rate of 1 over rate of 2 is equal to the radical molar mass of 2 over 1. Okay? Right here. You see how it's inverse? Right? Rate of effusion of gas 1 over rate of effusion of gas 2 is equal to the square root of M2 over M1, M representing the molar mass of whatever gas you are comparing. So let's compare. Let's do a quick comparison. If I want to compare the rate of nitrogen to the rate of chlorine, first of all, which one is going to move faster, nitrogen or chlorine? Nitrogen. Why? It's a lot lighter. Okay. So then that's going to be the radical molar mass of Cl2 over N2.
Wait, isn't it N2 over CO2?
You want
Inverse.
Yeah.
Inverse, right? All right. Cl2 is 71. N2 is 28.
Wait till smaller one.
Right?
Does it matter that the smaller one has to be on the bottom, or is it just like the opposite?
Well, if you're comparing the N2 to the Cl2 and you want to know how many times faster N2 is, that's why you start with the N2. Okay? So then what do you do in order to determine this? This is just a plug-in, right? 71 divided by 28, and you take the square root of that, and you get 1.3. 1.5.
Why don't you cross multiply?
There's nothing to cross multiply with. What are you cross multiplying with?
But don't you usually give us one rate and tell us find the other?
Sometimes. Not in this case. This is a comparison. When the rates are being compared, you're just saying this gas is faster than the other one, right? So if I'm comparing N2 to Cl2, then I can automatically say nitrogen effuses 1.59 times faster than chlorine. That's all you can say from that equation. Okay? Now,
You hit us with one on a test last year that was just that.
calculate the ratio of effusion rate of hydrogen and uranium hexafluoride, which is a gas used in the enrichment process to produce fuel for nuclear reactors. Okay? So it gives you a graph which shows you the percent of molecules at different speeds. Okay? And you can see obviously hydrogen is going to be at a different, faster speed, than UF6. Okay? So molar masses. So I'm going to compare hydrogen to uranium hexafluoride. It even sounds scary.
But even like just if you have anything with hydrogen in it, even if it's just hydrogen, like just regular hydrogen, is it not going to be the faster one regardless? Because
It's 2 grams.
I know,
Yeah.
exactly.
2 grams. Now you're comparing though. This is a comparison between one gas and the other. So I want to know how many times faster hydrogen is. And you can see hydrogen is going to move 13 times faster because UF6 has a molar mass of 352, whereas hydrogen is 2. Effuses. Effuses.
How do you, when you give us a practice problem like in a paragraph format, like how do you decide what goes on top and what goes along? Like how do you know?
You're comparing hydrogen to UF6,
The lighter one goes on top.
right? So if you don't put the lighter one on top, you can't say this many times faster,
So you probably calculate it first.
right?
How does it volume of the molecule?
Oh, like the single one? It's so tiny that it's not going to make a difference.
That just means that uranium hexafluoride diffuses 13.2 times faster than.
No.
No.
Hydrogen effuses 13 times faster. Uranium hexafluoride cannot effuse 13 times faster. Uranium hexafluoride is a big molecule, 352 grams per mole.
What if you ask?
Okay, so you got an elephant compared to a mouse.
What if you ask us how many times slower? I mean, how many times slower is it? It's the opposite question.
13 times slower.
It wasn't that satisfying.
No.
All right.
Wait, did you think she was going to give you another answer?
I don't know what I thought.
Okay, and the experiment for this, and we tried this, I don't know if you guys remember, did we try with you guys or maybe last year AP and it didn't work?
No, we tried.
Okay,
No, we
so what you
No, we
do,
did.
it didn't work, did it?
Omri did it and didn't.
I
Yeah.
gave it to you for like
Okay.
an hour.
Right? It
It
just-
did not work.
Wouldn't do it. I think it was a concentration. I think it has to be so concentrated that it becomes volatile. I don't have a really high concentration of ammonia. So what you do, you put a cotton ball with ammonia on one side and one with hydrochloric acid on the other side.
Oh, we did try that.
And then once it starts moving, right, on which side of the tube will you form ammonium chloride, which is a white solid? Are you going to form it closer to the HCl end or the NH3 end? How do you decide that?
The slower. Which one?
Which one takes closer to the heavier
So
one?
NH3 is going to move so much faster than HCl because NH3 is 17 grams, HCl is 36.5, right? So since this is going to effuse slower, so this is what it should have looked like, by the way. You would have this white cloud forming.
Yeah, no, we found the
That's
video
because
there.
ammonium chloride is a white cloud.
We found the
A
video.
white solid.
No,
It won't be in the middle. Why won't it be in the middle?
On the right
Because
side.
It will be closer to the heavier end because the heavy gas is the one that's going to move slower. Okay? So, you know, they're moving and they're going to meet each other in the middle, but they're not going to meet each other in the middle. One is moving a lot faster than the other.
Yeah, like when it's nice, Harry Potter, beautiful, and then the thing in the middle.
Hey, if it works, it works. All right. So, exhibited by real gases under condition of low pressure and high temperature is your ideal gas behavior. In other words, for gases to behave ideally, what does that mean for a gas to behave ideally? What is an ideal behavior?
It's at
It equals 22.4 liters.
no, that's ideal temperature.
That's standard. Ideal behavior. What is ideal behavior?
Doing what it's supposed to do.
Exactly. In terms of, for the gases, it's in terms of kinetic molecular theory. Kinetic molecular theory told you all these postulates. It should do this and it should do that. Well, if it's an ideal gas, it should follow all the postulates, right? And for that to happen, it would have to be low pressure and high temperature.
When you have high temperature, wouldn't you have a high pressure?
Not necessarily.
That's hard.
Right? Because if it's a large volume, it won't be. Because if it has a lot of space,
Yeah, it
even
wouldn't
if it's
have
high
any-
temperature, because it's taking up so much room that the collisions are less.
Got it.
Okay?
You wanna try it?
No, these two.
Sorry.
All right. So, when you plot PV equals nRT, right? There are certain ones that ideal. Your ideal gas is kind of right here, right? And as you increase pressure, and look at the increase in pressure though, guys. When we're talking about increase in pressure, 200 atm, 600 atm, those are huge amounts of pressure. Because atmospheric pressure is how much?
1.
So when I'm talking about 600 atm, I'm talking about 600 times the atmospheric pressure. So that's obviously a lot of pressure being exerted, right?
What's like outer space pressure? Out of curiosity.
Well, look it up.
Can I?
What kind of pressure do you have if you don't have molecules? All right.
Is there no pressure? Is it zero?
That's so
There's also
Vacuum.
no sound in space.
It's a
It's
vacuum.
1.322.
You don't have molecules.
10 to the negative 11.
All right. We don't do van der Waals equation. So you can ignore van der Waals equation. Once again, ignore van der Waals equation.
It's not a bio.
We'll talk about the interaction, but that's different than this. Okay. Let's wrap this up already.
Yes, gladly.
For a real gas, the actual observed pressure is lower than the pressure of the ideal. And the reason for that is intermolecular forces. Anyone remember what intermolecular forces are?
Dipole?
Yeah, that's one.
London.
London. What else?
Hydrogen
bonding?
That's it.
Right? So, molecules hold on to each other
I have really good notes.
because they have forces that hold on to each other. But what kind of forces do they have? Well, they have forces that are based on their bonding. They have forces based on their polarity, which we're going to look at. Okay? But we'll look at that in detail later on when we talk about the bonding as well. Atmosphere, you already know what it's made up of. Nitrogen is 78%, 21% is oxygen, and everything else makes up 1%, which is water vapor and carbon dioxide. Water vapor, carbon dioxide, methane are your three top greenhouse gases, right? The more they increase, obviously, the more the climate change we have. Okay? So, there's variation of temperature with altitude. We're not going to worry about it so much, but sea level, right? That's where I know we are. And then tropospheres, and then tropopause, and you have stratosphere, mesosphere, thermosphere, and exosphere. And exosphere, you're going up 1,000 kilometers above sea level.
So is that where you have to low mass?
Yeah, you don't have enough oxygen there. Oxygen decreases as you move up. The ozone layer is within the stratosphere. Ozone layer is what filters out UV radiation coming in.
You're like almost there when you're on a plane.
Isn't that what the global warming?
Like it's kind of close.
Yeah, but it's a supersonic plane.
No, but like,
Commercial aircraft flies about 10 kilometers above sea level. That's kind of your maximum altitude there.
Sorry.
Okay? Mount Everest goes up to about 8 kilometers above. But when you're climbing Mount Everest, if you've seen people who go mountain, mountain climbing, I guess, they have to have oxygen tanks after a certain elevation because the air is so thin up here, there's just not enough oxygen, they start getting delusional.
What elevation?
I don't know the max elevation where you have to actually use oxygen mask.
Why does the lack of oxygen
You don't have enough oxygen going to your brain cells, so you start getting delusional. Things happen. Yeah, kind of look up, mountain climbing.
Monday or Tuesday.
Really? Wow.
That's so soon.
Air pollution. We'll talk a little bit more about on Monday, 7:15.
That's bullying.
7:15 a.m. Monday.
How do I identify bullying? Pain. Heat. What is it?
Pressure.
Pressure.